This is quantitative methods, and this is the reading on probability concepts. This is quite a long reading. Let's not worry about the number of slides in this slide deck, well into the 40s. Let's just remember that statistics and now probability concepts is your friend. So let's embrace these topics. All right, the first LOS asks us to define a couple of things. Random variable, first of all, refers to any quantity with an uncertain expected future value. My children use that word random all the time. I really don't think they're using it in the proper way. Random means that you just can't predict what that future outcome is, like maybe the rate of return on a stock next year, the value of an index, or maybe even the exact date of death of an insured in a life insurance contract. An outcome refers to a possible value that random variable can take at some time in the future. Of course, the lottery ticket has two outcomes. You can either win or you can lose. A football game, you can either win or you can lose. A foul shot, you can either make it or you can miss it. An event is a specified outcome or a specified set of outcomes. For example, we could define a particular event like a return on a mutual fund is going to be 10% or less, and then event B would be if that return is more than 10%. Let's go ahead and look at the difference between mutual exclusivity and events that are exhaustive. Those of you who are married will know that you made a very important mutually exclusive decision at one time in your life when you said I do to your spouse. You said I don't to everybody else. So a mutually exclusive list of events can mean that only one of them has the possibility of occurring at any time. So for example, the return on a stock could be equal to 10%, or it could be less than 10%. So it's not possible to have both outcomes at the same time. On the other hand, exhaustive means exactly what the name suggests. It covers all possible outcomes. So if event A is 10% return on a stock and B is less than 10% and C is greater than 10%, well, then that includes all possible outcomes. What about probability? Probability is a number between 0 and 1. So it's 0% to 100% that a stated event will occur, right? I mean, everything has to occur with some probability. You can't be less than 0 and you can't be more than 100%. That's why I'm always fascinated by these sports athletes who say, I gave 110%. Not quite sure what that means. Think of it also as the probability. An example is the probability that a portfolio could earn a return below 10%. So a 0.6 probability means there is a 60% chance of that event happening. And then if there is an event that will occur with certainty, like the return on a treasury bill. If you buy a treasury bill today, you know you're going to get your principal amount from the U.S. Treasury Department because the U.S. Treasuries are considered to be default risk-free. So that's 100% probability. If an event is impossible, then that probability is 0%. For example, the National Basketball Association League is beginning its season this week. What's the probability that LeBron James is going to average 100 points a game? That's an impossibility. So probability of an event is going to be a number between 0 and 1, and the sum of those probabilities of mutually exclusive and exhaustive events equals 1, 100%. Now, probabilities can be empirical, which occurs from analyzing historical data. Subjective probabilities are personal beliefs or judgments, and a priori probabilities are subjective and deductive and kind of based on common sense, maybe some form of reasoning. And so an empirical probability example could be we look at a mutual fund for the last 20 years and we try to predict what's going to occur during the course of this year. And we can look at subjective probabilities. I could say to you, hey, I think LeBron James is going to average 31 points a game. That's just maybe my personal belief or my personal judgment. And then an a priori probability might be something like if we've got 2 applicants for a job and one has let's say a 60 or a 70% chance of getting that job offer, then the other candidate has either a 30 or a 40% chance. On to the next LOS, state the probability of an event in terms of odds. Here's where we need to be really careful between these two terms. Lots of times the words probability and odds are used interchangeably. And if they're referred to without any math, it's probably okay to substitute one for the other. But when there's math involved, you got to be very careful. They mean 2 different things and have 2 different interpretations. All right, the odds are going to be determined based on a ratio. So let me give you a quick example here. Suppose that there are 12 marbles in a bag. 6 green, 4 yellow, and 2 blue. And let's suppose that we want to determine what the probability of reaching into that bag and pulling out a yellow marble is. All right, the numerator is going to be the 4 yellow marbles in the bag divided by the total marbles in the bag, which is 12. So 4/12 is 33%. So that's the probability of selecting a yellow marble out of the bag filled with 12 marbles. Now, on the other hand, the probability, on the other hand, the odds for a yellow is going to be 4 yellow in the numerator again, and then 8 non-yellow in the denominator. You have 4 yellow and you have 6 green and 2 blue, so that's 4 in the numerator and 8 in the denominator, so that's 1 in 2. So make sure you can distinguish between a probability, which is going to be like 33% in this example, and the odds might be 1 in 2 or 1 in 1 or 1 in 5 or 1 in 10 or some number like that. And here are the formulas that the Institute gives you in their materials, but it's probably good to do just another quick example here. Let's see, an analyst believes that a stock's earnings per share will range from 20 cents to 35 cents next year. The odds that the stock beating its highest estimate of 35 cents are 1 in 9. All right, so those are the odds, 1 in 9, which was just like we said in the previous page. What was that? 1 in 2, right? So this is 1 in 9. So we're going to switch back and say, what is the probability that the stock will actually beat the highest estimate? And so we're going to use this formula there right in the middle of the page. Given odds 4E of A to B, so let's go ahead and do that there. So we're going to take the 1 in the numerator, and we're going to divide by 1 plus 9, which is 10, so 10%. So 1 out of 10 cases, we expect the stock to beat the highest estimate just 1 time. That's next year. So the next year in that question stem gives you that number. All right, how about the difference between unconditional and conditional probabilities? An unconditional probability is the probability that an event occurs without worrying about anything else that occurred beforehand. You might say something like, I think that my basement will flood. What is the unconditional probability that my basement will flood? Well, the flooding in your basement is probably close to 0, right? I mean, how many times do we ever have a flood in our basement? But when it rains, then there's an increase in that outcome. And so that's the difference between the unconditional probability, which is taking a look at the probability of an event without thinking about anything else. So without taking into account any other preceding events. These are standalone events. But conditional probabilities, this is going to be something like, it's going to sound something like, hey, what is the probability that my basement will flood if a hurricane sweeps through my area? Oh, now we have the hurricane and the flood in the basement, and those two things are linked. Now, we're going to talk in a few slides about correlations here, but clearly there's a relationship between rainfall and flooding in the basement. All right, so conditional probability describes the probability of an event A given that another event B has already occurred. So it's raining, it's raining, it's raining. What's the probability that that rain is going to seep into our basement? And there's a good formula there. Now there's some rules regarding these probabilities that we talked about on the previous slide. All right, multiplication rule. This is going to be a rule that helps us determine joint probability of two events occurring. And so a joint probability is the probability that two events occur together. Now, of course, there has to be some correlation between those two events. I mean, what's the joint probability of my son making a foul shot in a basketball game and the mail being delivered on time? That doesn't really make a whole lot of sense to kind of figure out that joint probability. But if we have some economic underlying principle that supports a relationship between those two probabilities of occurring, like the probability that both gas prices and bus fare increases will occur at the same time. And so the multiplication rule states that the probability of A and B occurring together, the gas prices and the bus fare increase, is the probability of the gas price given the bus fare and the probability of the bus fare. And then if A and B are independent events, you don't have to have the slash in there about conditionals. All right, a bag contains 16 blue and 14 yellow. Two balls are drawn from the bag at random. Two balls from at random, one after the other. So that's important. And then without replacement, that's important as well. So what will be the joint probability of both balls being blue? So let's think about the outcomes. You're drawing two balls, so first one could be blue, second one could be blue, first one could be yellow, second one could be yellow, first one could be blue, second one could be yellow, first one could be yellow, second one could be blue. So we're covering all those outcomes. So what's the probability, joint probability of them being blue? So the first ball has a probability of 16 out of 30 because there are 16 blue balls, right? And then the second one being blue, now there used to be 16 blue, now there's only 15. There used to be 30 total, now there's only 29. And so to get that joint probability, multiply those two together. So you got 15 over 29 times 16 over 30, and that gives you about almost 28%. Now, just like you can multiply, you can add. So for mutually exclusive events, the probability of A or B occurring is just the sum of the two probabilities. But for non-mutually exclusive events, we need to avoid counting that joint probability twice, because the probability of A and the probability of B, they include all of those things even when they intersect. So you subtract out the probability of A and B occurring. Quick example. CFA candidate is asked two questions. She gets the first question correct, has a 30% probability, and the second question correct is a 40% probability. Given that the probability that she gets both questions correct is 10%, what is the probability that she gets either the first, the second, or both questions correct? And so here we're going to take the 0.3 and the 0.4, so the 30% and the 40%, and then subtract out that 10%. So 60% that she doesn't make, what is that? That she doesn't make two mistakes, right? All right. Now, the total probability explains an unconditional probability of an event in terms of the event's conditional probabilities. And so here we have to distinguish between a scenario and then the complementary scenario. So that's why in the formula you'll have an S that will occur, that's scenario, just S, scenario S, and then a complementary scenario. And so there's a formula there that gives you that probability. We can use that total probability rule to determine unconditional probability in the event in terms of probabilities that are conditional on certain scenarios. So look at that formula there. If you have a set of mutually exclusive and of exhaustive events from S1 and S2 all the way out to Sn, then that total probability is the sum of all of those multiplications. Let's take a look at an example here. So what do we have? Two states of the economy, no recession and a recession. So note that the no recession is P and R with the complementary, with the C up there, and then the recession is just the probability of a recession. And those are 70% and 30%. And so what we're saying now is what happens if the economy goes into a recession or it doesn't go into a recession. And so the stock price in a recession can either rise or fall, and a stock price in no recession can either rise or fall. And those probabilities of a no recession during stock price performance during a no recession is 80% and 20%. And then a stock price performance during a recession is 30% and 70%. So here's the question. What is the total probability of a stock price increase? And so we're starting today with an estimate of probabilities of recessions and no recessions. That's 70 and 30%. And then we layer that with probabilities of stock price performance, which is either 80-20 or 30-70. All right, so how do we compute that? Well, all we're going to do is just a kind of a weighted average. We're going to take the 80% times the 70%, and we're going to add the 30% times the 30%, because we're going to ignore the possibility that the stock price could fall. And so we get 65%. How about the difference between dependent and independent events? Events are independent if when one occurs that has no bearing on the other occurring. Go back to my example about if my son makes a foul shot in the driveway, does that mean that the mail is going to be delivered on time? So those are two independent events. And so the example I have here is rolling a dice and flipping a coin. And so if you flip a coin, you get a heads. Does that mean you're going to roll 4 or 6? No. Doesn't have anything to do with each other. That's correlation of 0. But suppose you have a bag containing 8 green and 5 blue balls. If you draw a blue ball without replacing it, the probability of drawing another one changes because you drew a blue ball in the first time, because now there are fewer blue balls and there are fewer total balls. Okay, that's stuff that we talked about in a previous slide. So those are dependent events. How about conditional expectations? This is interesting, and it adds another level of our understanding of probabilities in terms of investment applications. And so what we're trying to do here is we're trying to use a set of real-world events that are going to influence some financial decision, like whether or not we should invest in a stock or whether or not a company should invest in a positive net present value project. And so if we wanted to, let's take a look at a company like Amazon. If we wanted to evaluate whether or not Amazon is a buy during this upcoming year, we would probably spend a lot of time looking at Amazon's financial statements. We'd try to estimate cash flows in the future. We'd look at their executive leadership, at their corporate governance structure. We'd look at their debt levels. We'd look at all that fundamental stuff, right? And so we could come up and say, hey, you know what? We think that Amazon is going to have, this dividend and this cash flow and this leadership. And because of all that, we think their stock price is going to be some number. But notice what that does is that ignores the rest of the environment, because that expected value of cash flows and dividends and stock prices is going to depend on some other stuff. Like what happens if suddenly Amazon gets more competition? Or the government comes out and says, you know what, Amazon, you're no longer allowed to deliver the next day. You have to deliver in 1 week's time. Or maybe financial institutions and maybe the Fed says we're going to raise interest rates 2 or 3%. So these other events, these other decisions by entities and institutions and organizations that have little to do with Amazon are going to affect that expected value. So continuous revision is needed. Total probability rule is useful. And then there's a good expected value formula. Let's take a look at a quick example. 20% chance that the government will impose a tariff. There's a timely example on imported cars. A company that assembles cars locally expects returns of 14% if the tariff is imposed and 11% if the tariff is not imposed. What is the unconditional expected return? All right, so think about what you have. You have two states of nature. You have one possibility is 14%, another possibility is 11%. So all we're going to do is we are going to, let's go back here, 20% chance. So all we're going to do is weight. We're going to weight those possibilities. So we're going to take the 11% times the 0.8 and then the 14% times the 0.2. So that's really a weighted average. And so this example is really good to help you understand that in dealing with probabilities, it's just like a weighted average. So what's our answer there? Around 11.5%. Tree diagrams. Here's where students tend to lose interest in statistics. But let me go ahead and give you a lecture that at level 2, clearly we're going to be using these tree diagrams to value a bond with an embedded option. So the sooner that you embrace these, as soon as you start loving tree diagrams, the better off you'll be. All right, so here's a visual representation of all possible future outcomes. All right, so here's the simple example. Let's suppose that we're going to toss a coin 2 times. All right, so here we are all the way at the left. So what do we know? We have a 50% chance of obtaining heads and a 50% chance of obtaining tails, right? And then regardless of what we get that first flip, we still have a 50% chance of a heads and tails at each node. So right where the H and the T are in the middle there, we're going to have another 50% chance. All right, so then notice what happens, that if we flip the coin twice and it comes up heads twice, that was a 25% chance. Go down to the bottom, 2 tails in a row is also a 25% choice. 25% chance or probability, as I show in the slide. And then you can either go up and down or down and up, heads, tails, or tails, heads, and those are 25%. So notice that you have 25 and 25 and 25 and 25. Was that 4? I think that was 4. So that adds to 1. The sum of the probabilities must add to 1. And the number of branches must represent the number of different possibilities. All right, let's look at an example here. All right, suppose we're investing in a defaulted bond issue. Oh boy. All right, so scenario 1 has a probability of 60% that we're going to recover 80 cents. And then that probability is 35% or a recovery of 70 cents per $1 principal with the probability of 65. All right, so do you see this? Scenario 1 then has a 60% chance. And then we have a 35 and a 65% chance of the second part. All right, so scenario 2 has a probability of 40%, and that recovery is 60, and then a recovery of 30 or 30%. What is the expected recovery? All right, so here we are all the way on the left. So we're going to start on the left, and we're going to say, all right, what's going to happen? We have 2 scenarios. We were given those initial probabilities as 60% and 40%. All right, so we go back to the coin flip, and our initial probabilities were 50% and 50%. Here, they're different than 50%. All right, so scenario 1 and scenario 2 have a 60 and 40% chance of occurring. Then, if scenario 1 occurs, then we have a 35% chance of getting 80 cents and a 65% chance of getting 70 cents. So think about this. Scenario 1 is better, right? Scenario 1 has a better outcome. We might get 80, we might get 70. Scenario 2 is the lesser of the outcomes. And if scenario 2 occurs, we have a 70% chance and a 30% chance of getting either 60 cents or 30 cents. So clearly, we would prefer scenario 1 to scenario 2. Now, let's figure out those probabilities. Let me go back here. Notice that in that far right column, those probabilities were 25, 25, 25, and 25 because 0.5 times 0.5 is 25, right? So come down here, we're going to do the same thing. We have if we recover 80 cents, all we're doing is multiplying those top two probabilities. So 35% times 60% is 21%. And then 60 times 65% is 39%. So we have 39% chance of getting 70 cents and a 21% chance of getting 80 cents. And you do the same thing on the bottom. All right, so the question then becomes, what do you expect to get out of this? So I want you to look at that far right column. You have those four possibilities. So all we're going to do really is multiply those four possibilities by their probabilities. And we're going to come up with that 64.5 cents. All right, so to do this step by step, like the study guide shows you, let's take the 35% times 80 plus the 65% times 70. That gets us to 73.5. And then let's take the 70% probability times 60 cents and the 30% probability times the 30 cents. That gets us to 51. And then we have to weight those. Remember I was saying this is like a weighted average. We're going to weight those by the 60% and the 40% original probability. So think about that we're just kind of working backwards. It's kind of like discounting in time value of money. We're working backwards from the future to the present to get 64.5 cents. All right, let's switch over to portfolio analysis. Boy, what is the expected value of a random variable? It's probability weighted. So there, again, I said something about probabilities. And so all we're going to do is multiply the probabilities by each possible outcome. To calculate the variance of that random variable, what we're going to do is take the difference between each possible outcome and subtract it from its mean. And we're going to square that difference, and we'll take the square root of it to compute what we call the standard deviation. And so we typically don't use variance in terms of a numerical description of the risk of an asset because you don't go to the food store and buy 12 pounds squared of potatoes. So we have to square the number to get the variance, so we take the square root to get it back down to its regular normal base, and for investments it's going to be in a percent. I'll show you a quick example here. Here's a probability distribution of a company's sales. All right, so there's a 20% chance that the company will generate 50 million in sales, 30% chance that the company will generate 40 million in sales, and a 50% chance that the company will produce 30 million in sales. Notice once again, in several of our examples, the probabilities must sum to 1. And then what we're going to do is just compute the mean and the standard deviation of those sales. All right, the fact that, here, let's do this. If the sales were 50, 50, and 50 instead of 50, 40, and 30, then the mean would be 50. That makes perfect sense. And the standard deviation would be 0. All right, but they're not. They're 50, 40, and 30, so let's compute both of those things. All right, so let's do a weighted average. So we're just going to multiply the probability times the sales. So 20 times 50 and 30 times 40 and 50 times 30. That gets us to 37 million. Now, I wish that I could give you a shortcut in your financial calculator that would enable you to compute the variance and then the standard deviation. But unfortunately, with probabilities, it's just not possible. You have to do this the long way. So get out your gloves, put your gloves on, get out the shovel. We're going to do a lot of financial digging here. All right, so all we're going to do is take each possible sales, 50, 40, and 30, and we're going to subtract that from the 37. So we're going to do 50 minus the 37, and 40 minus the 37, and 30 minus the 37. Notice in the formula there, I just have expected sales. So that's going to be the 37 in there, and we'll multiply that by the probabilities. All right, so what are those probabilities? 20%, and 30% and 50%. So we get 61 million. But that's like coming home and saying to your husband or wife, hey, I bought 12 squared pounds of potatoes. Well, he or she probably has no idea how many potatoes you bought. So you take the square root of it to get almost 8 million standard deviation. So expected value is the mean. That's the first moment of the distribution. And the standard deviation is a measure of risk. That's the second moment of the distribution. All right, how about covariance and correlation? So notice back here, when we calculated the variance, what we did is we took each possible value minus its mean value or its expected value, and then we squared it. And that's because we were just doing this against the sales, so we had to square it to get rid of the negative. But with covariance, what we're trying to do here is measure the degree of co-riskiness or co-movement between two random variables. So instead of squaring a term, we're going to multiply it by another term. So look at the formula there. The covariance between x and y is the expected value of each possible x minus its mean times each possible y minus its mean. And that's where we get covariance. And then if you substitute returns there, that's the bottom formula. So how do we interpret covariance? Covariance is a random variable, could take on almost any value. But positive covariance means that the returns move together. The random variables move together. So if one variable goes up by 10%, then the other variable is going to go up. Maybe it'll go up by 3%, maybe it'll go up by 14%, but it's still going to go up. And then the opposite is true with a negative covariance. That means that if one goes up by, let's say, 10%, the other one is going to go down. Maybe go down by 3% or go down by 14%. We don't know what that number is, but we know that it's going to be an indirect relationship. And then zero covariance means that they're not related, meaning that if one goes up by 10%, then the other one could go up or down or up or down or up or down. You just don't know. There's no relationship. Now, remember what I just said. Covariance is it's a random variable, and it can take on almost any value. But what statisticians like to do is they like to take random variables and squeeze them down into a more meaningful range. And that's what statisticians have done with the covariance. Covariance, let me go back to that formula there. That covariance, that could be almost anything. It could be a minus 100. It could be a plus 4,000. It could be 0.444. Right? And what does that mean? Well, it's difficult to interpret a covariance. But when we standardize the covariance by dividing it by the product of the two standard deviations, we get something called the correlation coefficient. And that correlation coefficient is a standardized random variable that's going to take on a value of -1 to +1. So how do we interpret that? A +1 correlation between two variables means that, are you ready for this? That if one stock goes up by 10% and the other stock has a 1.0 positive correlation, that means that other stock is going to go up by 10% on average. Not every day, but on average. A -1 correlation coefficient means the opposite, that if stock 1 goes up by 10%, then stock 2 is going to go down by 10% on average over time. And then a zero correlation means no relationship as well. So remember that correlation measures the strength and the direction of a relationship. So if correlations are nearing 1, like 0.9 or 0.85, that means there's a really strong relationship. Maybe the returns of two companies like Walmart and Target, both in the same business, both in the same industry, they both sell the same types of stuff, they probably have a pretty high correlation. Now, you might have to be exposed to what's known as a correlation or a covariance matrix. And so this is just going to be a matrix which is going to look at three assets, A, B, and C, and down the diagonal terms. Notice that in the diagonal terms from top left to bottom right, covariance between the return on A and the return on A, and then covariance of the return on B and the return on B, and covariance between the return on C and the return on C. Those are the variance terms. So the covariance matrix has the variances on the diagonal. But on the non-diagonal terms, those are going to be the covariance. So look at the intersection of A and B, covariance between RB and RA, et cetera, et cetera. And you can do this with correlations as well. All right, on to the next LOS. Calculate the return and the variance of a portfolio. Now, you got lots and lots of formulas to memorize, but this one shouldn't be too bad. So the expected return on a portfolio is just a weighted average. We've done that several times so far. But the variance of the portfolio is going to be a little bit different. We're going to have to take the weights and we're going to have to square them. We're going to have to take the standard deviations and we're going to have to square them. And then we're going to have to consider the covariance. And this is really important for moving on. The reason that we add that covariance term to the right-hand side of the variance formula is to reflect the value of diversification. We'll talk about this at length in another video. But now just remember that we're taking those weighted averages, but they're squared terms initially, and then that third term on the right is really a diversification term. And I have the two formulas there. The first one has the covariance as the far right last term, and the second formula has the covariance in the far right term, but I substituted it with, where was that formula there? Let's go back here. So instead of covariance, I have the correlation times the two standard deviations. All right, so let's take a look at an example. Let's suppose we have two mutual funds, A and B, and we've got 60% invested in A, which means there must be 40% invested in B. A has a 15% return, and B has a 10% return. There's the covariance matrix. So notice that the covariance between A and A is 400. That translates into a 20% standard deviation. And then the 169, that's a 13% standard deviation for B. And then, so tell us what the standard deviation of the portfolio is. All right, so here we go. We're going to take the weighted average. So we're going to do 60% times 15 and 40% times 10. So there's the expected return. That's just a weighted average, so that's okay. Just as a quick reminder, if we invested half of our wealth in each, 50% and 50%, then that expected return would be 12.5, right? Half of 15 and half of 7. Then the variance, we're going to take the probability, the weight in A, which is 60%, times that variance of 400, and then 40% squared times the variance of B, which is 13%, or 169. Just leave it in that form, because I think the Institute gives it to you in these forms. And then we're going to do 2 times 60% and 40% wealth in each of those assets times the covariance between A and B, which is going to be the same number, right? The covariance between A and B is 80, then therefore the covariance between B and A has to be 80. So if you do the math, you get about 14.5%. All right, how about Bayes' formula? This is really interesting, and this formula, what it looks relatively complex on the slide there, but it's really not. It's named after this dude Bayes, who is widely respected and widely used in not only finance but also medicine and engineering. There are probabilities that it sounds something like this. What we want to do is calculate a probability given a set of prior probabilities for a given event that are updated, that reflect current information. Like going back to my example with LeBron James averaging, what did I say? I think LeBron is going to average 31 points a game this year. Well, if during the first 20 games of the season, LeBron averages 40 games a year, well, then that probability changes. So this Bayes probability allows you to update. All right, here's an example. Let's see. An engineer wishes to investigate the punctuality of electric trains by considering a number of train journeys. All right. 50% of the trains had a destination for New York, 30% to Las Vegas, 20% to Washington, D.C. All right, so notice the sample. There's 50 and 30 and 20. That adds to 100. All right. The probability of the trains arriving late are 40, 35, and 25. So what does that tell us? New York has the worst on-time probability of arriving on time, right? And Washington the best. All right, if the engineer picks a train at random, what is the probability that it's late in New York? All right, so there's that big old formula. Let me go back here. We're going to just use that formula in blue, and we're going to substitute with some new notation. We're going to say N is an event that goes to New York, V is Vegas, and W is Washington. All right, so we're looking at the probability that it arrives in New York and it's late. So let's use the notation L as the notation for a randomly chosen train arrives late. All right, so randomly chosen. All right, so the probability that the New York is going to be late by random selection. Notice in the numerator, what we're doing is we're taking the probability that we pick New York, right? Well, let's go back here real quick. So the probability that a train arriving late in New York is 40%, and the probability that any train in the sample goes to New York is 50%. So that numerator is the 50% of the trains go to New York and 40% of the trains are late that go to New York. So that's the numerator. And then the denominator is the sum of all of that same thing. So all we're doing is repeating the summation of Las Vegas and Washington in the denominator, and we're going to sum them. So notice we have that same 50%, 50% times 40. And so let's go back here. What did we say? Vegas has 30% of the sample, and 35% of them are late. So there's the 30 times 35. And then the Washington, D.C., 20% of the sample. And then what's that, 25%? So there you go. You get about 56.3%. All right, the counting problems here. What we're trying to do here is figure out how we can arrange a portfolio in different ways. I mean, this is the great application of the counting issue or counting theory. You know, if you have, let's just take a simple example. If you have 10 stocks, how can you arrange them in groups of 2 that have different levels of risk? So you have 10 stocks, they each have different levels of risk, but you group them into similar risks. So how can you arrange them? How many different ways can you arrange them? So those are the kind of questions that we're trying to ask. So what example do I give you there? We might be interested in the number of ways we can choose 7 stocks comprising 3 small cap and 4 large cap stocks from a group of 50 stocks. All right. So there are several of these ways to count. So using factorial, combination, and permutation concepts. So factorial, I think you learned factorial back, I think I learned this back in the 8th grade, if I remember correctly. So all we're doing, n factorial simply means it's the product of the first n natural numbers. So n factorial is n times n minus 1 times n minus 2, etc., etc. And so 1 factorial is 1 times 1, and 3 factorial is 3 times 2 times 1. The labeling, this is what I was talking about with the different risk classes in that example of the 10 stocks. And so labeling is the principle to assign k labels or groups to a total number of items in which each label contains a certain number of items. You wish to categorize into k groups. And there's the formula there. You take the n factorial and put that in the numerator, and then you divide by the product of the n's all the way up to k. So here's an example here. Suppose you have a portfolio consists of 10 stocks. You wish to assign 3 different labels so that label 1 has 5 high return stocks, label 2 has 3 medium return stocks, and label 2 and the last label has 2 low returns. So you got 3 different labels. You have 5 stocks in label 1, 3 stocks in label 2, and 2 stocks. So there are your 10 stocks. All right. So the solution, n is 10, right? We know that. And there are 3 labels. So n1, n2, and n3 are 5, 3, and 2. And so all we're going to do to figure out how many different ways we can assign those 3 labels is take the 10 factorial in the numerator and then divide by the lowercase n's. So the n in the numerator is the uppercase n, and the n's in the denominator are the lowercase n. So 5 times 3 times 2. So that's 2,520 different ways. Now, clearly, the Institute doesn't want you to do 2,520 ways of arranging these stocks, but it gives you a sense of all of the possibilities, because those 10 stocks, they might be appropriate for, let's say 5 different clients, but you need to rearrange them in 5 different ways. All right, how about combinations? This is basically a selection of some items given items where the order does not matter. All right, so there's a good formula there. So let's take a look at an example. How many ways can we choose 3 stocks from a portfolio consisting of 10 stocks? So this is different than part 2. Let's go back here real quick. Part 2, what was that? We were labeling, so we were categorizing or classifying those. Here, we're just saying how can we choose 3 stocks? All right, so all we're going to do is take that 10 factorial and divide by 7 times 3 factorial. That gives us 120. So it's 10 factorial over 10 minus 3 factorial times 3 factorial. 120. And then permutations, and so here the difference between combinations means the order doesn't matter, but permutations means that the order does matter. And so let's go ahead and take a look at an example. You ready for this one? How many ways can we choose 3 stocks from a portfolio consisting of 10 stocks in order to execute a sale if the order is paramount? And so all we're going to do here is remove, let's go back to this one. Notice that in the denominator we have n minus r factorial times r factorial. Here we're just taking out the r factorial. So 10 factorial over 7 factorial is 720. Now, here's the advice that you need. How do you determine which of these approaches to take on the exam? So here are some 4 good bullet points. If you're asked to assign n items to n slots, use factorial. In case you are asked to assign k labels or categorize into n items, use the labeling formula. Use the combination formula when the order is not important to choose from among a sample. And then if the order is important, choose the permutation formula. So I think those 4 bullet points in combination with your memorization of those 4 formulas. Did I hit all those? Yeah, I hit all those 4 formulas. Okay. And that completes our fun section on probability concepts. Now we'll do distributions next time.